Hello everyone, my name is Ankit Mahur. I am a student professor in IIMT College of Engineering, Greater Noida. In today's lecture, I am going to discuss about differential equation. Today's lecture based on introduction of differential equations, order and degree of differential equations, formation of differential equations, complete solution of linear differential equation with constant coefficient by different method finding particular integral, general method to finding solution. So, to start with definition, an equation involving derivatives or differential of one or more dependent variable with respect to one or more independent variable is called a differential equation. There are two types of differential equation. First is ordinary differential equation and second is partial differential equations. So some examples: dy equal x plus sin x dx. This is example of ordinary differential equations. Again, example of d power 4 x upon dt power 4 plus d square x upon dt square plus dx upon dt whole power 5 equal e power t. This is also example of ordinary differential equation. Example third and example four are example of partial differential equations. Del square u upon del x square plus del square u upon del y square plus del square u upon del z equals 0, where x and y are two independent variables. So this is an example of partial differential equations. So now I am going to discuss about order and degree of differential equation. The first is order. The order of the highest order derivative involved in a differential equation is called the order of the differential equation. And what is degree? The degree of a differential equation is the degree of the highest derivative which occur in it after the differential equation has been made free from radical and fractions as far as the derivative are concerned. So some example is d square y upon x square minus 4 dy upon x minus 5 y equal x e power minus x. So this is order of 2 and degree is 1. And the example is x square cube d cube y upon d square cube plus x square d square y upon d square plus x dy upon x plus y equal x plus log x. So this is an example of order 3 and degree 1. Now I am going to discuss about linear and non-linear differential equations. A differential equation is called linear if every dependent variable and every derivative involved occur in the first degree only, and no product of dependent variables or its derivatives occur. That is, if a differential equation satisfies the given two conditions, then differential equation is said to be linear differential. Otherwise, differential equation is said non-linear differential. So now I am going to discuss about solution of differential equation. General or complete solution of nth order differential equation will have n arbitrary constants. An order of differential equation number of constants in solutions. So discuss about some examples. Eliminate the arbitrary constant a and b from the equation y equal e power x, a cos x plus b sin x, and obtain the differential equations. Here a and b are arbitrary constant. So we have the relation y equal e power x, a cos x plus b sin x, where a and b are arbitrary constant. So first differential with respect to x. So we get y dash equal e power x, a cos x plus b sin x plus e power x minus a sin x plus b cos x. This is the value of y. So the given equation can be written as y dash equal y plus e power x minus a sin x plus b cos x. Now again differential of equations 2. We get the equations y double dash equal y dash plus e power x minus a sin x plus b cos x plus e power x minus a cos x minus b sin x. So using equation 1 and 2, we get y double dash equal y dash plus y dash minus y. Solve this, we get y double dash minus 2y dash plus 2y equals 0, which is free from a and b. So this is the required solution. So now I am going to discuss about linear differential equation with constant coefficient. So a differential equation of the form a naught d power n by dx power n plus a1 d power n minus y upon d x power n minus 1 plus a2 d power n minus 2y upon dx power n minus 2 up to a and y equals x. where x is a function of x only and a naught, a1, an up to an all are constant. The given equation can be written as a naught d power n plus a1 d power n minus 1 plus a2 d power n minus 2 up to a n y. So now the general solution is y equals cf plus pi, where cf is complementary function and pi is particular integral, where cf involves an arbitrary constant and pi does not involve any arbitrary constants. Now I am going to discuss about working group for finding complementary functions. So we first write the equation in symbolic form f dy equal x. Write auxiliary equation, namely fm equal 0, which will be an algebraic equation of n and d. A naught m power n plus a1 m power n minus 1 plus a2 m power n minus 2 up to an. So replace d by m and y equal 1, we get the auxiliary equations. On solving the auxiliary equation, we shall get n roots. Three case arises according as the roots of the auxiliary equation. Now I am going to discuss about case first when roots are real. First, suppose that the auxiliary equation has n distinct roots. Let m1, m2, mn all are distinct and real roots. Then CF is C1 e power m1x plus C2 e power m2x plus C3 e power m6 up to Cn e power m1x. And suppose that the auxiliary roots has n equal roots, let m1 equal m2 up to mn. Both roots are equal. Then CF is C1 plus C2x plus C3x up to Cnx or n minus e power m1x. Now I am going to discuss about some example which is based on real roots. So solve d square minus 5d plus 6y equals 0. First we write auxiliary equation. Replace d by m and y equal 1. We get m square minus 5m plus 6 equals 0. Solve the equation m square minus 5m plus 6. We get the values of m equal 2 and 3. We see that all the roots 2 and 3 are distinct. Then CF is C1 C1 e power 2x plus C2 e power 3x. Since here x equals 0, so the general solution is y equals C1 e power 2x plus C2 e power 3x. Now discuss about case third, complex roots. So let the alpha plus minus iota beta be the complex root, where alpha beta both are real. Then CF is e power alpha x C1 cos beta x plus C2 sin beta x. This also can be written as C1 e power alpha x cos beta x plus 2 or C1 e power alpha x sin beta x plus 2. If roots are repeated, let alpha plus minus iota beta and alpha plus minus iota beta with two equal complex roots. Then CF is e power alpha x C1 plus x C2 cos beta x C3 plus x C4 sin beta x, where C1, C2, C3, C4 all are arbitrary constants. So discuss some examples. Solve d square minus 2d plus 5 equals 0. So first we write auxiliary equation, replace d by m and y equal 1. So m square minus 2m plus 5 equal 0. Replace d by m and y equal 1. So we get auxiliary equations. Solve the auxiliary equation, we get the roots m equal plus minus 2 iota. Here both the roots are complex roots. Then CF is e power x C1 cos 2x plus C2 sin 2x. Since here x equals 0, that is pi equals to 0. So the general solution is y equal e power x C1 cos 2x plus C2 sin 2x. Now I am going to discuss about case third when roots are third roots. So let alpha plus minus root beta be a third root. Then CF is e power alpha x C1 cos hyperbolic root beta x plus C2 sin hyperbolic root beta x. When roots are repeated, let alpha plus minus root beta and alpha plus minus root beta two equal roots. Then CF is e power alpha x C1 plus x C2 cos hyperbolic root beta x plus C3 x C4 sin hyperbolic root beta x, where C1, C2, C3, C4 all are arbitrary constants. to discuss some example which is based on third rules. To solve d square minus 4d plus 1y equals 0. So first we write auxiliary equation. Replace d by m and y equal 1. We get the auxiliary equation d square minus 4d plus 1 equals 0. So solve m square minus 4m plus 1. We get the values of m is 2 plus minus 2, 3. So both the roots are third roots. Then CF is e power 2x c1 cos hyperbolic root 3x plus c2 sin hyperbolic root 3x. Since x equals 0, so the general solution is y equal e power 2x c1 cos hyperbolic root 3x plus c2 sin hyperbolic root 3x. So now I am going to discuss about particular integral. So let the given differential equations be a naught d power n plus a1 d power n minus 1 plus a2 d power n minus 2 up to a n y equal x or f d y equal x. Then pi is 1 upon f d x. So now I am going to discuss about working rule for finding pi. That is formula first when x is the form of e power ax, then pi is 1 upon fd e power ax. So first replace d by a, then we get 1 upon fa e power x, where fa not equal 0. If fa equals to 0, then multiply by x and differential of denominator with respect to d. So we get pi equals to x 1 upon f dash d e power ax, or x 1 upon f dash a e power x, where f dash a not equal 0. So discuss some examples. Solve d square y upon x square minus 3 dy upon dx plus 2y equal e power 3x. So first we write equation in symbolic form. D square minus 3d plus 2y equal e power 3x. So the auxiliary equation is replace d by m and y equal 1. So we get m square minus 3m plus 2 equals 0. Solve m square minus 3m plus 2 equals 0. The value of m is 1 and 2. Both the roots are real and distinct. Then CF is C1 e power x plus C2 e power 2x. And PI is 1 upon d square minus 3d plus 2 e power 3x. So replace d by 3. So we get 1 upon 3 square minus 3 into 3 plus 2 e power 3x. Solve this, we get 1 upon 2 e power 3x. Then solution is y equals CF plus PI, where CF is complementary function and PI is particular integral. So CF is C1 e power x plus C2 e power 2x and PI is 1 upon 2 e power 3x. So now I'm going to discuss about example 2. So solve dq minus 5d square plus 70 minus 3 y equal e power 2x cos hyperbolic x. The auxiliary equation is replace d by m and y equal 1. So we get m cube minus 5m square plus 7m minus 3 equal 0. So solve this. The value of m is 1, 1 and 3. So two roots are equal. Then CF is C1 plus C2x e power x plus C3 e power 3x. C1, C2, C3 all are arbitrary constant. And Pi is 1 upon d cube minus 5d square plus 70 minus 3 e power 2x cos hyperbolic x. So first we had cos hyperbolic x is e power x plus e power minus x upon 2, and multiply e power 2x into e power x upon 2 and multiply e power 2x into e power minus x upon 2. So we get 1 upon d cube minus 5d square plus 70 minus 3 e power 3x upon 2 plus e power x upon 2. So first replace d by 3 and first replace d by 3. So if we replace d equals 3, so the denominator equals to 0. Then multiply by x and differential of the denominator with respect to d. So we get differential of dq is minus 3d square, differential of minus 5d square is minus 10d, and differential of 7d is 7. Similarly, replace d equal 1. If replace d equal 1, the denominator equals to 0. Then multiply by x and differential of denominator with respect to d. So we get differential of dq is 3d square, differential of minus 5d square is minus 10d, differential of 7d is 7. So if we replace d equal 3, we get 1 upon 3 into 3 square minus 10 to 3 plus 7 e power 3x upon 2. And again replace d equal 1. So denominator equals to 0. Now again multiply by x and differential of 3d square minus 10d plus 7, which is equal to minus 60 minus 10. So replace d equals to 1. So we get the solution is x e power 3x upon 8 x square 1 upon 6 into 1 minus 10 e power x upon 2, which is equals to x e power 3x upon 8 minus x square e power x upon 2. So the general solution is y equals cf plus pi, where cf is c1 plus c2x e power x plus c3 e power 3x, and pi is x e power 3x upon 8 minus x square e power 3x upon 8. Now I'm going to discuss about case second, when x is sin x plus b or cos x plus b form. So pi is 1 upon fd square sin x plus b. So first replace d square equals to minus का a square, provided f minus a square not equal 0. If f minus a square equals to 0, then pi is multiplied by x and differential of denominator with respect to d. So which is equals to x 1 upon f dash d square sin x plus b. So replace d square equals to minus a square. So we get x 1 upon f dash minus a square sin ax plus b, provided f dash minus a square not equals to 0. So discuss some example. So solve d square minus 2d plus 1 y equal cos 3x. So first we get auxiliary equation, replace d by m and y equal 1. So we get the equation m square minus 2m plus 1 equals to 0. Solve this, we get the values of m equal 1 comma 1. So both the roots are real and repeated. So then cf is c1 plus c2x e power x, and pi is 1 upon d square minus 2d plus 1 cos 3x. Replace d equal 1. So replace d square equals to minus a square. So we get 1 upon minus a square minus 2d plus 1 cos 3x. So if we solve minus 1 upon 2, 1 upon d plus 4 cos 3x, so first realize d minus 4, which is equals to minus 1 upon 2 d minus 4 d square minus 16 cos 3x. Replace d square equals to minus a square. So we get minus 1 upon 2 d minus 4 upon minus a square minus 16 cos 3x. Solve this, minus a square minus 16. So we get the value of 50. So 1 upon 50 d minus 4 cos 3x. Multiply d equals to cos 3x and 4 equal cos 3x. So we get 1 upon 50 d cos 3x minus 4 cos 3x. So differential of cos 3x is minus 3 sin 3x and minus 4 cos 3x. Then solution is y equals cf plus pi, where cf is c1 plus c2x e power x and pi is 1 upon 50 minus 3 sin 3x minus 4 cos 3x. So another example is solve d square plus 4 y equals sin square x. Then the auxiliary equation is m square plus 4 equals to 0. Solve m square plus 4, we get the values of m is plus minus 2 iota. So then cf is c1 cos 2x plus c2 sin 2x, and pi is 1 upon d square plus 4 sin square x. So sin square x equals to 1 minus cos 2x upon 2. So solve this, we get 1 upon 2 1 upon d square plus 4 e power 0x minus 1 upon d square plus 4 cos 2x. First replace d equal 0 and replace d square equals to minus a square. If replace d square equals to minus a square, the denominator equals to 0. So differential with respect to d and multiply by x, then which is equals to 1 upon 2 into 1 upon 4 minus x 1 upon 4 sin 2x. Solve this, we get the values of 1 upon 8 1 minus x sin 2x. So the complete solution is y equals cf plus pi, where cf is c1 cos 2x plus c2 sin 2x, where c1 c2 are arbitrary constant, and pi is 1 upon 8 1 minus x sin 2x. Now I am going to discuss about case third, when x equal x power m or polynomial or degree m, where m being positive integer. So step 1 is take out lowest degree term from fd to make the first term unity, and the remaining factor will be of the form 1 plus fd or 1 minus fd. So and step 2 is take this factor in the numerator, that is pi equals to 1 upon 1 plus minus fd x power m, or it can be written as 1 plus minus fd whole power minus 1 x power m. Step third is step third is expand. It is ascending power of d as far as the term containing d power n. And step 4 is operate on x power m term by term. Some expression which are used in these questions. So 1 plus x power minus 1 is 1 minus x plus square minus x plus cube up to infinity. And 1 minus x power minus 1 is 1 plus x plus square x cube and so infinity. So discuss some examples. Find the pi of d square plus 5d plus 4 yx square plus 7x plus 9. Then pi is 1 upon d square plus 5d plus 4x square plus 7x plus 9. First, common the lowest degree term, that is 4. So we get 1 upon 1 plus 1 upon 4d d square plus 5d. So x square plus 7x plus 9. So it can be written as 1 upon 4, 1 plus 1 upon 4 d square plus 5d whole power minus 1 x square plus 7x plus 9. So expand 1 plus x power minus 1, which is equals to 1 minus x plus x square. Here x is 1 upon 4 d square plus 5d. This is equals to, so 1 upon 4, 1 minus 1 upon 4 d square plus 5d plus 1 upon 16 d power 4 plus 25 d square plus 10 d cube up to and so on x square plus 7x plus 9. So multiply this. This is first, this is second, this is third. So we get 1 upon 4 x square plus 7x plus 9 minus 1 upon 4 d square x square plus 7x plus 9 minus 1 5 by 4 d x square plus 7x plus 9 plus 1 upon 16 25 d square x square plus 7x plus 9. All the terms are neglected because the d of highest power. So now, so 1 upon 4 x square plus 7x plus 9 minus 1 upon 4 into 2 minus 5 by 4 2x plus 7 1 upon 16 25 and into 2, which is equals to 1 upon 4 x square plus 9 upon 2x plus 23 upon 8. So which is the required solution. So discuss another examples. Solve d cube minus d square minus 60y x square plus 1. The auxiliary equation is m cube minus m square minus 6m equals 0. So replace d by m and y equal 1. So solve m cube minus m square minus 6m equals 0. So we get the values m equals 0, 3 or minus 2. So all the values are testing and real. Then CF is C1 plus C2 e power 3x plus C3 e power minus 2x. And PI is 1 upon d cube minus d square minus C3 x square plus 1. So first, common the lowest degree term, that is minus 60. So which is equals to 1 upon minus 60, 1 plus 1 upon 6 d minus d square plus 1. So which is equals to 1 upon minus 60, 1 plus 1 upon 6 d minus d square whole power minus x square plus 1. This is the form of 1 plus x power minus 1. So this expansion is 1 minus x plus x square. Here x is 1 upon 6 d minus d ka whole square. So we get 1 upon minus 6d, 1 minus 1 upon 6 d minus d square plus 1 upon 36 d minus d square and so on. Square plus 1. So multiply of this x square plus 1, which is equals to 1 upon 60, 1 minus 1 upon 6 d minus d square plus 1 upon 36. So we get the whole square is d square plus d power 4 minus 2d cube up to x square and so on into x square plus 1. So multiply by x square plus 1. So we get 1 upon minus 60 x square plus 1 minus 1 upon 60 x square plus 1 minus d square x square plus 1 plus 1 upon 36 d square x square plus 1. So if we solve, then we get 1 upon minus 60 x square minus 1 upon 3x plus 25 upon d 25 upon 18. So 1 upon this integral of this. So we get 1 upon 6 x cube upon x minus square upon 6 plus 25 upon 18x. So this is the final pi. So the complete solution is y equals cf plus pi, where cf is complementary function and cf is c1 plus c2 e power 3x plus c3 e power minus 2x and pi is minus 1 upon 18x cube minus square upon 2 plus 25 upon 6x. So thank you for watching.